Nutrients are chemical elements and compounds required by the biosphere for its proper functioning. Nutrient balance refers to the accounting under various time scales of the source, transport, and fate of nutrients in ecosystems, both natural and artificial. The characteristics of the nutrient balance determine the success or failure of artificial ecosystems, upon which humans depend for food and fiber. As shown here, even for natural ecosystems, the nutrient balance is paramount. The flat pulse is the annual seasonal flooding of relatively flat, low-lying areas adjacent to major rivers. The flood pulse is conditioned by the local climate and geomorphology. In turn, the nutrient balance is affected by the flood pulse. In these ecosystems, geology, geomorphology, hydrology, and ecology are intertwined in such a way that it is impossible to separate them. They must be considered as a whole, in effect amounting to a holistic ecosystem analysis. Among the essential nutrients, nitrogen stands out because of its wide availability. Molecular nitrogen constitutes 78% of the Earth's atmosphere. Nitrogen cycles through the biosphere by way of 5 biochemical processes. 1. Fixation. 2. Ammonification. 3. Nitrification. 4. Assimilation. And 5. Denitrification. Under fixation, nitrogen enters the biosphere through A. The action of lightning, B. The mediation of nitrogen-fixing bacteria, and C. In developed societies through industrial processes. Under ammonification, decaying organic matter is converted into gaseous ammonium compounds. Under nitrification, ammonium compounds are converted, that is, oxidized, to solid state, first into nitrites and later to nitrates. Under assimilation, plants uptake nitrates from the substrate, where they become available for recycling. Finally, under denitrification, nitrates are converted, that is, reduced, through a series of intermediate steps to molecular nitrogen, which escapes to the atmosphere, thus closing the nitrogen cycle. Clearly, the fifth process, denitrification, is required to close the nitrogen cycle, returning the nitrogen to the atmosphere, where it originated. Significantly, the absence of denitrification will have the effect of opening the nitrogen cycle. Under this scenario, the nitrogen will tend to accumulate in the lithosphere, where it becomes available for harvest as a component of food and fiber, if necessary. On the other hand, effective denitrification will close the nitrogen cycle, thus inhibiting nitrogen accumulation and impairing the possibility of harvesting. Natural ecosystems are subject to natural laws. Artificial ecosystems such as agriculture, particularly irrigated agriculture, have social and economic constraints which translate into practices or laws. Export of nutrients is an established practice in the management of artificial ecosystems. Nutrient export cannot proceed in the presence of effective nitrogen cycling. In the absence of external inputs, a naturally denitrifying ecosystem will not work well for agriculture because the nitrogen will be lost, that is, returned to the atmosphere, and thus not available for export. Where are these denitrifying ecosystems apparently unsuited for agriculture? There are certain flood pulse ecosystems in which the combination of climate, geology, geomorphology, and hydrology is such that it encourages denitrification. Alternating periods of aerobiosis and anaerobiosis in a natural ecosystem will lead to nitrification, followed by denitrification, and thus the eventual return of nitrogen to the atmosphere. Aerobiosis occurs during the dry season. anaerobiosis during the wet flooding season, if the latter is long enough. An annual flood pulse, with a sequence of dry and wet periods lasting approximately 6 months each, will have a tendency to close the nitrogen cycle. Note that the rate of oxygen diffusion in water is 10,000 times smaller than that in air. When oxygen is forced to diffuse through water-saturated pores, this restriction in oxygen transport quickly leads to anaerobic conditions. Anthropogenic nutrient export will be difficult under these circumstances. The denitrifying ecosystems may be well suited for uses such as cattle grazing and wildlife habitat, but not for intensive export agriculture. This figure shows that nitrate reduction, resulting in denitrification, is the second in a series of various different biochemical reactions taking place in wetland ecosystems, ranging from oxygen reduction at high positive values of redox potential, 800 millivolts, to methanogenesis at low negative values, minus 400 millivolts. From this figure, it is concluded that denitrification is more common in wetlands than methanogenesis. This is understandable, since the latter is the last in the series, involving the reduction of the organic matter itself. Based on the above premises, a first exclusion principle regarding nutrient balance under flood pulse may be stated as follows. Flood pulse ecosystems are naturally not conducive to intensive export agriculture. A singular example of this principle is represented by the aboriginal cultural geography of the Llanos de Mojos in Beni, Bolivia. The native pre-Hispanic population of the Llanos de Mojos knew that their lands were too flat and subject to extended seasonal flooding. Throughout the years, they learned that the only way to open the nitrogen cycle, thus making possible nutrient export, was to build the raised fields, or camellones. These anthropogenic features of the landscape sought to causeway the flood in order to keep portions of the land sufficiently dry throughout most, if not the entire year. The number and aerial extent of these raised mound fields attest to the ingenuity and perseverance of the early peoples of the Llanos de Mojos. In 1966, Denevan estimated a minimum of 100,000 drained fields occupying 15,000 acres spread unevenly over an area of 30,000 square miles in the western Beni. Such example of agricultural engineering on a massive scale shows how humans in this part of the world were able to survive despite seemingly insurmountable odds. A second exclusion principle, which does not involve human action or need, may be stated as follows. In flood pulse ecosystems, the survival of woody vegetation hinges upon their symbiotic relationship with hummocks. The application of this principle is embodied in the distinctive hummocks which exist in the Florida Everglades, the Pantanal of Mato Grosso, and the floodplain of the Araguaia River, to name a few. A hummock is an island of woody vegetation within the great expanse of seasonally flooded herbaceous plains. Generally, trees cannot establish themselves from seed in continually wet soil. Therefore, it is surmised that the islands formed through the Quaternary period by progressive sedimentation, enabling the colonization of the floodplain by woody vegetation. Moreover, the nitrogen cycle was opened, enabling nutrient accumulation and export, albeit somewhat limited under browsing by wildlife. Opening the nitrogen cycle is a prerequisite for the sustenance of ecosystems, both natural and artificial, that depend on this nutrient for their survival and/or subsequent export. Two related exclusion principles are formulated. 1. Flood pulse ecosystems are naturally not conducive to intensive export agriculture. And 2. In flood pulse ecosystems, the survival of woody vegetation hinges upon their symbiotic relationship with hummocks. The camellones of the Llanos de Mojos are an excellent example of the first principle. The hummocks of the Everglades, the Pantanal of Mato Grosso, and the floodplain of the Araguaia River are clear examples of the second principle. Additional research on the nitrogen cycle, including the all-important denitrification stage, should throw more light on the workings of nature and their emulation by humans.